All right, in the previous couple of videos, we saw lots of examples about applied optimization, and they all kind of followed the same steps once you got the hang of it, but it was sort of hard to figure out those steps, right? I mean, the idea is you need to figure out the function and the constraint. Typically, the function is two variables, but the constraint allows you to rewrite that function in terms of one variable. And then it's just using stuff you learned in the past about finding and classifying critical values. We looked at examples about like fencing land and building boxes and stuff. But really, maybe those aren't the applications that you care at all about. Maybe since this is a business calculus class, it makes more sense to look at applications towards business. And that's what we're going to do in this video and the next. And it turns out that these examples can absolutely be two variable as well. And it's certainly possible to give the student a constraint and allow them to rewrite their function in terms of one variable like we did in the previous couple of videos. However, following the lead of your book, I'm not going to do that. What I'm going to do for these business applications is start you out with a one variable function. The reason why is we learned in these previous videos how to get a constraint and change a function into one variable. You already know how to do that. What I really want to get across in these videos is a lot of vocabulary and concepts specific to business. And I'm afraid that if I do the constraint to variable thing, those ideas might get lost. So while the examples in this video could look more like the ones that were a little bit more challenging in the previous videos, they're not going to in our class. So let's start with kind of a more basic example. Suppose we have a cost function, C of X. C represents the cost and X is the number of units. So think the total cost of producing X units. If I was only producing, I don't know, 1 unit, I change all the X's into ones, and I would get that the total cost is $2,541, I guess. And if I wanted to know the total cost of producing, say, 100 units, I just change all the X's into 100s. If you have a function that tells you cost, you might be interested in what's called marginal cost. So this function is telling you the total cost of all, say, 100 units. The marginal cost is just focusing on the cost of that next unit. The marginal cost for the 100th unit, you can kind of think about that as how much it costs to produce 100 units minus how much it costs to produce 99 units. That change in the total amount of cost represents the marginal cost. But maybe you don't want the marginal cost just for the 100th unit. You want a function that tells you the marginal cost for any amount of units. Well, since the marginal cost is the change in the total amount of cost, maybe it makes sense that the marginal cost is just going to be C prime of X. So C of X is given up here. To figure out C prime of X, we just take the derivative. The derivative of 2500 is 0. The derivative of 40X is 40. And the derivative of X squared is 2X. This is a function that tells us the additional cost for any extra unit. If we want to know the additional cost for the 100th unit, in other words, the marginal cost of the 100th unit, we just have to evaluate C prime of 100. It would be 40 plus 2 times 100. It would be $240. Minor nitpicky point here, really this is continuous, whereas the way I described this is more discrete. When I looked at the difference between the 99th and the 100th unit, the way I described it is kind of the average rate of change from 99 to 100, and really what we're calculating is the instantaneous rate of change with C prime of X. I described it in terms of secant lines with points really close, but really what we're calculating are tangent lines and their slopes, but you don't have to worry about any of that. In an applied setting, they essentially mean the same thing, and I'm only differentiating them because I feel guilty technically lying to you, even if it doesn't really matter. Anyways, the point is just if we have a cost function, you might be interested in the marginal cost. And when you see the word marginal, just think derivative. The marginal cost is just the derivative of the cost function. And once you know the marginal cost, you can evaluate things like the marginal cost of the 100th unit by just evaluating the derivative at 100. Marginal cost is very useful to figure out, but it's not the only thing related to the cost function we might be interested in. You might be interested in the average cost, right? This is the total cost of any number of units, but how much is each of those units actually costing me? Well, it depends on how many units I produce. The average cost, maybe AC can represent that, is just the total cost, C of X in this case, divided by X, the number of units that I'm producing, right? The total divided by how many you have gives you the average. C of X is 2500 plus 40X plus X squared, and I want to divide that by X, and that gives me the function for the average cost. I can figure out the average cost for any number of units. If I produce 10 units, how much is each one costing me? If I produce 5,000 units, how much is each one costing me? I might be asked a question like, what is the average cost of the first 100 units? Well, that's just evaluating this function, AC of x, at the point 100. AC of 100 would be 2,500 plus 40 times 100 plus 100 squared, and then divided by 100. Let's see, this is 4,000 and this is 10,000, so that's 14,000. I think I get 16,500 up in the numerator, and I got 100 in the denominator, so it looks like I get 165 as my average cost per unit for the first 100 units. So the first thing I want to make clear here is the difference between marginal cost and average cost. Marginal cost is the derivative of the total cost function. Average cost is the total cost function divided by the number of units we're producing, x. And if those aren't confusing now, they get a little bit more confusing when you're asked questions like, how do we minimize the average cost of our units being produced? When you see the word minimize, maybe you're thinking optimization. If so, that's fantastic. If we want to minimize any function, what we do is we look for the critical values. So I have AC of x up here. What I want to know is AC prime of x. I take this function right here and figure out its derivative. I could take the derivative the way it's written right now, or I could rewrite this so I don't have to use the quotient rule. Maybe just to remind you of the quotient rule, I'll use that. The derivative of the top would be 40 plus 2x, and I'll multiply that by the bottom, which is x. From that, I want to subtract the derivative of the bottom, which is just 1, multiplied by the top, which is 2,500, plus 40x plus x squared. But then I got to remember I'm not done. I got to divide that entire thing by the bottom, which is x squared. If I simplify this thing a little bit, I got 40x plus 2x squared in this term. And then from that, I want to subtract 2,500. I want to subtract 40x, and I want to subtract x squared. And that entire thing is divided by x squared. Combining like terms, I got 2x squared minus 1x squared, so I got x squared. I got 40x minus 40x, so those go away. And then I have this negative 2,500. Divide that whole thing by x squared, and I've got the derivative of my average cost function. Now that I have the derivative, I can figure out critical values. I'm a little bit low on room, so maybe I can do that up here. I find critical values for any function by taking the derivative of that function and setting it equal to 0. So if I want the critical values for my average cost function, I take this function's derivative, which we just figured out, and set it equal to 0. X squared minus 2,500 divided by x squared equals 0. If we multiply both sides by x squared, I get x squared minus 2,500 equals 0. So x squared is equal to 2,500. So x is either plus or minus the square root of 2,500. X represents the number of units that we produce. It doesn't make sense to produce a negative number of units, so the only relevant solution is positive square root of 2,500, and the square root of 2,500 is just 50, so we get x equals 50 for our critical value. Technically, this critical value could be the minimal average cost, or it could be the maximal average cost. So technically, I should take the second derivative and plug this in to make sure that the second derivative is positive at this point, so that I know my function's concave up, so that I know that this critical value represents a minimum. Again, it always will in this section, but I feel a little guilty not doing it, so I'll do it even though you don't really have to. To classify that critical value, I need to know the second derivative as a function of x. I know the first derivative as a function of x, I guess down here. I could take the derivative of this thing, or I could rewrite that thing and then take the derivative. Maybe that'll make the calculus a little bit easier. I can think about this as x squared over x squared, in other words, 1, minus 2,500 over x squared, in other words, 2,500 times x to the negative 2 power. In this form, it's a little bit easier to take the derivative. The derivative of 1 is just 0, and the derivative of negative 2,500 x to the negative 2. I bring the negative 2 down in front, and I get 5,000 x to the negative 3 power. In other words, 5,000 divided by x cubed. If I evaluate this second derivative, when x is equal to 50, I get 5,000 divided by 50 cubed. And I don't know what that number is. Actually, I think I do. I could cancel out the thousands and the thousands. I get 5 divided by 5 cubed. I'd get 1 over 25, I think. But really, I don't even care what this number is. I can just look at this and tell that this is a positive number, which is really all that matters. That tells me that my average cost function is concave up when x equals 50. So that critical value at 50 is a local minimum. And since I'm looking to minimize my average cost, I'm very happy, and I know that this is really my answer. All of this dealt with cost functions, But really in a business setting, you're not just interested in the cost, you're also interested in the revenue. So maybe I'll also look at a revenue function, maybe an oversimplified revenue function, where we're selling our goods for $200 each. If you're selling these things for $200 each, then our revenue as a function of X is just 200 times X. If we sell, 15 units, the amount of revenue we make is 200 times 15. Suppose you had this really simple revenue function and you were asked to figure out marginal revenue and average revenue. Well, for marginal revenue, when you see this word marginal, just think the change in revenue. For change in, you're thinking derivative. So I just got to figure out R prime of X. R prime of X is just the derivative of this function, which is super easy. It's just equal to 200. Oh yeah, that makes sense. If I'm selling these things for $200 each, then the amount of money I make by selling one more unit is always equal to 200, no matter how many units that I've sold. What about average revenue? Well, average revenue, just like average cost, is total revenue divided by the number that I sell. So I'll take my total revenue, my 200x, and I'll divide that by the number that I sell, x in this case. 200x over x is just equal to 200. My average revenue is just 200. Yeah, it doesn't matter how many you sell. If you're making 200 for each, the average amount that you make is always going to be equal to 200. In this case, because our revenue function is super simple, our marginal revenue ends up being 200 and our average revenue ends up being 200 no matter what our value of x is equal to. Why did I bother with this? Well, because now that we have a cost function and a revenue function, we can talk about profit. You may have heard that profit is maximized when marginal cost equals marginal revenue. This is a phrase that gets thrown around a lot in business classes. Why do you want marginal cost to equal marginal revenue? The answer is because profit is just revenue minus cost, right? The amount that you profit is what you bring in minus what you spend. Suppose you wanted to maximize your profit. Well, when you're maximizing anything, you're thinking optimization. When you're thinking optimization, you're thinking I need to find critical values. To find critical values, you'd have to take a derivative. You take p prime of x here. The derivative of the difference in these two functions, well, I got two terms, so I take the derivative of the first one, and then I take the derivative of the second one, and I subtract those two things. I get critical values when the derivative is equal to 0. So I get critical values when 0 is revenue prime x minus cost prime x. To maximize profit, you take the derivative of profit and set it equal to 0. But the derivative of profit is just the derivative of revenue minus the derivative of cost. So profit is going to be maximized when the difference in the derivative of revenue and the derivative of cost equals 0. But when the difference between the two equals 0, they equal each other, right? Add c prime of x to both sides of the equation, and you get r prime of x equals c prime of x. In other words, profit is maximized when marginal cost equals marginal revenue. This phrase is really just teaching you optimization. It's saying that the way you figure out optimal, maximum in this case, profit is by taking the derivative of the profit function and setting it equal to 0. You want to see that in action? Sure. Profit is revenue minus cost. Revenue is 200x, given by our revenue function right here. Cost is 2500 plus 40x plus x squared, given by our cost function up here. So the profit that we make from producing x units is 200x minus 2500 plus 40x plus x squared. We can clean this up a little bit by distributing this negative through the parentheses and combining like terms. I got negative x squared, 200x and negative 40x nets out to 160x minus 2500. My profit as a function of x is given by this expression. If I want to maximize profit, I need to find critical values. To find critical values, I take the derivative of this profit function. The derivative of this profit function would be negative 2x plus 160. For critical values, I take that derivative and set it equal to 0. So I got 0 equals negative 2x plus 160. In other words, 2x is equal to 160. In other words, x is equal to 80. I could, if I wanted to, take the second derivative of my profit function, which would be the derivative of this function, which would just be negative 2, and then evaluate that second derivative at my critical value to figure out that my profit function is concave down when the amount of goods that I'm producing, x, is equal to 80, and therefore 80 is a local max. But because of the way these problems work out, we kind of already knew that that was what was going to happen here. If my cost and revenue functions are as given above, then I maximize profit by producing exactly 80 units. Note that when I'm producing 80 units, my marginal revenue is equal to 200, and my marginal cost would just be C prime of 80, which is 40 plus 2 times 80, which is 40 plus 160, which is 200. My marginal cost is 200, my marginal revenue is 200 at this critical value where I'm maximizing profit. I'm really figuring out the exact same thing two different ways, as I kind of tried to prove to you over here in pink. I think that's plenty of info for this video, so why don't I call this one good and we'll do one more.